Welcome to Titans of CNC PCSC edition. I'm the instructor, Briston Trapp, and welcome to the programming of Titan Building Block 5M. First, we're going to go ahead and check our model. Make sure your hole is countersunk, depth 0.3, diameter 0.25, tip angle 118 degrees, countersink diameter 0.265, 90 degree countersunk. Click OK. First, I'm going to go to Preferences. I'm going to turn off my tooltips because I forgot to do that. That will make it a little better for the viewing pleasure of this video. Thread should be 1/4-20, and we don't want a thread model. And let's just double check our hole again, make sure that your depth is 0.3, diameter 0.25, countersinked 0.265. Remember to suppress your chamfers because we really don't need these. When we go into the model, to the cam, suppress feature. We have the logo of the Titan Eagle imported as a DXF. You can also sketch your own text on here with a new sketch. Text. I don't know why the text is upside down sometimes. Go ahead and rotate it and position it, and then you can go through the font, size, angle, click OK. Right click on the text, and I'm going to explode it. And now we'll turn that solid text into a set of sketch geometry. Stop sketch. Cam workspace. In your setup, pretty similar to before, milling operation, our work coordinate system is going to be front, left, top corner of the stock. So that's model orientation, Z up, X to the right, Y backwards. Origin is going to be the stock box point, and then we're picking this front, top, left corner. Our stock is going to be fixed size box, X width 2.05, Y 2, Z 1, and like always, offset from the top 0.03. Post processor 5001, 5M S1 with your initials, and we're using work offset number 1 for G54. First operation is going to be our facing operation with our 2.4 inch shell mill. As before, just like always, 3500 RPM, 100 inches a minute. This should be copied from previous Titan building blocks, so there's really nothing here that needs to be changed or edited. Could make it 180 degrees if you want your shell mill to start on the left and go to the right. 0 will have it start on the right and go to the left. After we deck off the top of the shell mill, we need to do some 3/8 flat end mill 3D adaptive. We're going to do 3D adaptive because we have multiple heights for our 2.5D part. I also had the coolant disabled on the facing operation, so you can make sure we can really see that shell mill. I'm going to go ahead and select the tool number 2, 3/8 flat end mill. This can be copied from Titan building block 4M. Going to go ahead, you can turn off the coolant on this since most of all our cuttings on the outside, we don't have to worry about chip evacuation, so you can really actually see what that end mill is doing. 6,000 RPM, We're going to have a feed per tooth of 6 thou. That's going to give us a cutting feed rate of 108 inches a minute. Lead in 90, lead out 90, ramp and plunge 30 inches a minute. We're going to do rest machining from previous operations. Height's going to be, bottom height is going to be model bottom, negative 25 thousandths. We're going to overshoot, make sure we go past our thickness of our model. And then the top height's the model top, retract height's model top 0.2, clearance height's model top 0.4. Passes, our tolerance is going to be 1/1000th of an inch. Optimal load 0.1125, which is 30% of the 3/8 flat end mill tool diameter. Minimum cutting radius 0.01. Maximum roughing step down 1 inch. That's the length of our flute on our 3/8 flat end mill. Fine step down is going to be 0.1. Flat area detection needs to be on. Minimum step down 0.01. Stock to leave is going to be 25 thousandths radial stock. Axial stock is going to be 10 thousandths. Smoothing is going to be turned on at 2 thousandths. That will smooth out our G code, make our G code less lines of code. Passes, linking now is going to be full retraction. This should all be pretty much the same. Stay down level is going to be most. Non-engagement feed rate 200 inches a minute. Don't really need to worry about our ramping since we're entering from the outside of the part. Click OK. Notice it takes a while to load. Go ahead and look at our toolpath. You should see 2 different layers. If you notice any really small like whisper cuts kind of in a non-efficient method of machining, you need to go back and make sure you increase the radial stock to leave. Next operation is going to be our standard 2D contour outside with the 3/8 flat end mill, 6,000 RPM, 60 inches a minute. Flood coolant. Bottom chains our selection. Height's basically the standard. Bottom height's going to be the selected contours, negative 5 thousandths. Passes, we're going to do in control, repeat finish pass. This is all kind of standard from previous Titan building blocks. And the linking, 45 degrees, pretty much standard like always. Next thing, in order to clean up this inside area, we need to switch to a smaller end mill because the 3/8 flat end mill cannot reach in there. So we need to first set up a 1/4 inch flat end mill. In your tool library, you're going to create a new tool. You're clicking on this button right here. Make sure you're adding it to your Haas master library. If you add it to your documents, not that big of a deal. General, it's going to be a 1/4 inch by 1 inch by 3 inch end mill. Most important thing is a 1/4 inch. Now ignore Kennemental, ignore that. Cutter, flat end mill, inches, 3 flutes, clockwise spindle rotation, like always. Carbide, no through tool coolant. The diameter is going to be 0.25. Flute length 1 inch. Shoulder length 1.1. Shaft diameter 1/4 inch. Body length 1.175. Overall length 3 inches. Critical dimension on all this being the diameter. And then also we want to make sure we have enough flute length. It's definitely enough. We're probably even going to use a end mill that has a little bit shorter flute length, maybe like 3/4 of an inch, but it really doesn't matter. Shaft doesn't matter, holder doesn't matter. Feeds and speeds, it's actually going to be 6,000 RPM and probably about 60 inches a minute. We'll finalize that during your operations. Post processor is going to be tool number 3. Comment is going to be 1/4 inch flat end mill. You click cancel, you click OK, cancel. So for that operation 2D contour, you're going to click on the 3/8 flat, the 1/4 inch flat end mill, flood coolant. It's going to be 6,000 RPM, 40 inches a minute, plunging at 20. Geometry is going to be this selection for the chain. Stock contours is going to be the outside selection for the cylinder. This is pretty much standard. Tolerance 4/10. Compensation type in control. Compensation radius 0.0125. Multiple finish passes. Number of finish passes is going to be 1. Step over is going to be 15 thousandths. Finish feed rate 40 inches a minute. We're going to do roughing passes. This will eliminate the need to do a pocket operation, so we're going to do a maximum step over of 0.2. Smoothing deviation of 4 thousandths. Number of step overs 3. Linking, everything in here should be fine. Click OK. So that will give us our essentially a pocket to clean this area, and then we have our finish pass right here to clean up the wall of the star. And now for the holes, we're going to go and use our 5/16 spot drill from Titan 2M, 5,000 RPM, plunging at 20 inches a minute. Geometries of selected faces. Height's going to be, the bottom height is going to be the whole top minus 0.1. That will give us our correct countersink depth. Whole top is the top height. The feed height is going to be whole top 0.1. The retract height is going to be model top 0.2. And the clearance height is model top 0.4. And this will be drilling rapid out. Drilling with the 228 drill for a 1/4 20 roll tap is going to be flood coolant, 5,000 RPM, 40 inches a minute. Geometries of selected faces. Bottom height is going to be whole bottom, drill tip through bottom. That should get our drill tip almost to the bottom of the part, but not through it. Top height is going to be whole top. Feed height is going to be whole top 0.1. Retract height, model top 0.2. Clearance height is going to be model top 0.4. Cycle type is going to be chip breaking, partial retract. Pecking depth 0.2. Minimum pecking depth 0.2. Accumulated 0.57. Chip break distance about 4 thousandths. Click OK. Next operation is going to be the 1/4 20 roll tap, and make sure you select the right tap. If you select the 1032 tap, it's going to rip out the threads and possibly break the tap. So it's the 1/4-0.05 right tap flood coolant. I'm actually going to bump this up to actually 1,000 RPM. Geometries of selected faces. Height's going to be, bottom height is going to be whole top negative 0.26. Top height's going to be whole top. Feed height's whole top 0.1. Retract height is going to be model top 0.2. Clearance height model top 0.4. Right tapping. Click OK. And now we're going to do the tracing operation for the eagle and this T. Edit. We're going to use our 5/16 90-degree spot drill to do the tracing. It's going to be a tracing operation, which is in the 2D drop-down menu under Trace. The engrave feature is something different. Use the trace one. So select our tool, flood cool, it's going to go 3000 RPM, and then all our feed rates are going to be nice and slow at 10 inches per minute. Geometry is going to be your selected chains. Notice the arrow is right down the middle of the line. There's no left side or right side. Heights are basically fine. You're going to go feed height is going to be model top 0.05, retract height model top 0.1, clearance height model top 0.2. Passes, basically the important thing on this is going to be our axial offset. This is going to control the depth of the engraving. So we're going to go down -5 thousandths of an inch, and linking is fine. Click OK. And our last operation, copied from previous Titan building blocks, is going to be our 10 thou edge brake chamfer, 4000 RPM, with tool number 9 1/4 inch flat tip chamfer. We're going to slow it down a little bit. We've been seeing a little bit of chatter, so we're going to cut at 50 inches a minute. Geometries, those selected features. Heights are standard. Passes going to be chamfer width 0.01, chamfer tip offset 0.08 with 2 thousandths of chamfer clearance. Linking is fine. Click OK. And for your simulation, I'm going to turn off the model. Simulate. Facing. 3D adaptive. Contour on the outside. There's our 2D contour with roughing passes with a step over. There's our spot drill, drill, tap. There's our engraving and our chamfer. Boom. Make sure you go transparent, and let's make sure that we have clearance between the bottom of our hole and the bottom of our tap. And that is basically it for programming. You want to make sure you got your setup done correctly. In review, work coordinate system is going to be front, left, top corner of our stock, and then we need to make sure that we have 30 thousandths on the top, a lot of material on the bottom for our talon grips, and our tool numbers are: tool number 1 is the shell mill, tool number 2 is the 3/8 flat end mill, tool number 3 is the 1/4 inch diameter end mill, tool number 4 is the spot drill, tool number 5 is the number 1 drill bit, tool number 6 is the tap, tool number 4 is going to be our 5/16 spot drill used for engraving, the trace feature, and tool number 9 is our chamfer. When you go to post-process, make sure you post-process either on the pre-next generation control, which I do believe works on both mills. But if you're going to use the next generation post processor for the super mini mill, make sure you actually use the super mini mill, because if you use the regular mini mill, this post processor will generate a feed rate of 650 inches a minute, and it will result in a over feed rate error. Post. Save this on my desktop, and our G code should consist of Tool 1, 2, 3, 4, 5, 6, and 9. Facing. Adaptive. And it looks like we got about 1,196 lines of G code. Remember to always save your work frequently. Thank you for watching, and good luck.